everybody. I hope everyone's having a wonderful day. So last day I'd given you the algorithm for removing a record from an AVL tree. So remember, we're going to apply the remove operation from the binary search tree which we've inherited. And then all we're going to do is we're going to start from the parent of the remove node and we're going to potentially have to rebalance the tree. So the way it works in my pseudocode is that you perform the remove operation, then you let V be the node where the remove node used to be. That was C prime in my pseudocode. And then all I did was I apply removeAVL, which should be recomputing the height, assuming that it's an internal node. And then it goes right up to its parent, and then it checks if it's rebalanced, matching the description up here. So what we're going to do is I'm going to do an example with you. And this is a little bit more of a complicated example because I really want to illustrate the ideas that we've been talking about. So what we're going to do is I'm going to remove 20 from this binary search tree. So what would be, how would I do that? How would I do that here? How do I do that? So if I remove 20, remember 20 is right here, right? It's right there. So notice I have two internal children. So they're both internal nodes. What do? That means I'm going to go to my right and I'm going to pick the smallest, using the smallest operation, then I'm going to copy its contents. So I'm going to take these the 25 here, and I better put this record information here. Then I'm going to perform delete on this. So I'm going to remove operation on this right here. So what's going to happen? Well, I need to remove this, but notice that both its children are leaves, right? So one of these is going to be my C, and the other one's C prime. And then what? Well, if this was P in the remove algorithm, then this is P prime right here, right? So what did it say to do? Remember what I did the other day? I just look at this and say, okay, well, there's C prime. I'm just going to take this over here and I'm just going to move whatever's there up to here. So what should it look like after I do the removal? Well, I should have 25 here. C prime ends up being right here. The train is excited. I'm not sure if you can hear the train, but the train is definitely booming. So as a result of the removal, we end up with the following tree. So note the heights of these nodes are 0, height of that's 1, height of this one was 2. Now remember that the height of C prime was 0, and the height that it has currently sitting in here is 3. So what's going to happen is we're going to now carry out rebalance AVL, and what we're going to do is what rebalance AVL will do is it computes the height if this was an internal node, then it goes where? It goes up to its parent, and then it checks the height balance property, right? But notice that 2 and 0, that differs by more than 1. So that means there's an imbalance occurring here. So I have Z here. Now what's just the tallest of these two children of Z? Well, it better be this one, right? What's the taller of these two? It's 15. So what kind of rotation are we going to do? Well, we need to go left, then right. So that means what kind of rotation? An LR rotation, right? So we need to perform an LR rotation. Let's do that rotation. Remember, this is a double rotation that we're doing. So we're going to do an LR rotation on this tree. In particular, we're going to be applying it from X twice, right? Remember, we push X, we promote X, then we demote Y, and then we're going to, after that, promote X again, but demote Z. So here we go. So what is this going to look like? Well, let me draw the right half of the tree quickly. That's not going to really change. 5, 45, 60, 40, 50, and then I think I have 65 right here, and then I have 35 in the left here. That 3 is kind of melting, kind of melted in the microwave. The whole node just kind of melted in the microwave, okay? It melted in the microwave. So what's going to happen here? So we're going to do what I had mentioned the other day. So remember, we're going to promote X, and then we're going to demote Y. That means it's going to go do this, and then it's going to trade this subtree and move it over to that side, okay? So what happens after that? So I'm going to promote X, demote Y, and then I'm going to push X up and bring Z down onto the other side. So what's that going to look like? What's that going to look like? Well, we know right away that the root of this subtree is going to be what? It's going to be 15, right? So 15, what's on its left? Well, it should be the one that we originally demoted, which is 10. And the one on the right should be what? 25. And that completes the LR rotation. The heights of these nodes didn't change. Remember, as you do these rotate operations, you'd make sure you update the height. Just make sure you check that the node exists where you need to update it, okay? So what's the height of 25 is 1. The height of 10 is 2. So those need to be updated at some point before I'm going to do the following. So now I perform the double rotation. Now I update the height of 15, which is now 2, right? Or is it 3? Actually, see, this is why you need to make sure you update. This is 1, because remember, 10 was 2 before, right? It changed, because I demoted it. So now the height would be correctly 2. I do these things on purpose to make sure you see that the steps for which we update the heights is very, very important. So just for the sake of importance, I'm going to make sure I update the heights in each one of, I forgot a leaf there, 2, 3, 2, and I think I forgot a leaf again. Actually, I think I forgot a leaf 2 places. 2, and then this is 4. So what do? We're done with this node. We go up to its parent after we recomputed the height here, and we check the height balance property, right? Is it satisfied? No, right? It differs by more than 1. So what kind of thing is happening here? So I'm going to perform. So that's Z, right? Well, that's really poor. Let me fix that. At Z, which is the taller of these 2 children of Z. This one is 55. What's the taller of these 2? Well, it is 45. So what kind of rotation do I need to do? What kind of rotation? I need to do a right-left rotation, right? Because it goes that way. So I need to go, because I go right, then left. At least in terms of how I determine the tallest of their children, okay? So remember, it's always determined by how tall the child is. So we always pick the taller of the 2, and if there's a tie, you always pick the one that's on the same side. Just to avoid double rotations, you can use a single rotation instead. So I have RL rotation. Now, what should you expect? So we've already done a double rotation a couple of times. So what should you expect? What should be the root of this tree? it should be 45, right? 45, remember? Because we promote X, demote Y, and then we're going to promote X again and demote Z. So what should you expect? What should be the left child of 45? Because I demote 30, it should be on the left. Because now, since I promoted 45, that means that on its right better be 55. Remember, you got to look at it like I move it like this, and then I push this up and push that down. And you got to remember, you don't want to lose track of those subtrees that are getting tossed around like weights on a scale. So what's going to happen? When I demote 30, what was going on? Well, I already knew on its left, I had this subtree, right? That one didn't change, right? 15, 10, 25, and I have my leaves. 1, 2. Okay, how about on the right? Is there anything that happened over here? Well, when I promote X, the right subtree goes where? Where did it go? Where does it go? Okay, I promoted 45. So 45, then what would happen? 50 would go along with where? What would happen? What happens to 50? Well, it goes along with 55, right? Because you got to imagine this gets demoted, then this subtree gets clung on to 55, and then it all goes up. What happens to the left subtree? Where does it go? This, right here. Remember our melted 35 and this 40. Where did that go? Eventually it's going to end up being on the right here. Remember, just try to visualize this in your head if possible. If not, break it into 2 steps. Just think of each one as a rotate operation. I don't expect you to figure this out right away unless you really catch on to this. But be aware that once you get a good grasp of this, you should be able to see intuitively how to do this. However, what I usually do is I always just think of rotating twice and just thinking about where these subtrees go as that happens. Because that's the trickiest part of trying to do this. So on the left, I end up with 50. On the right, what's on the right? Well, we should still have that right subtree, right? That should still be there. This is how I remembered it. 0, 0, 0, 1, 2, 1. These all get updated as we do the rotate operations. Okay, so now I've finished doing the RL rotation. Now what do I need to do? I just have to update the height of this node here. What is it? It should be 4. Now, I have reached the root of the tree after this, and thus I have finished the rebalancing. Now you can see that we have an AVL tree. And we're done. So isn't that neat? So the big trick here is just remembering to identify what rotation you have to apply if an imbalance occurs. And I recommend identifying these 3 vertices. It tells you exactly what kind of rotation you should use. I'm just getting excited about this. And remember, you just got to imagine it like I promote X, demote Y, and then I'm going to promote X again, which is pushing this up and putting that down, and it's going to trade over one of the subtrees in between. But remember, when you first promote it and demote it, it's going to trade off one of these over to the right subtree. Okay? So that's all I have to really say about removals. Let's talk about generally some properties of AVL trees that I really should stress. So as you can see in this example, it wasn't the case that only one rotation was needed. You needed to do multiple ones. Do you see why? Because the tree, I could literally remove the node from anywhere in the tree. And when I perform that second deletion, that can happen anywhere along the tree where I perform this removal, and that can cause a cascade of imbalances like in this example. Either way, a good bound on that is indeed the height, which we know is log n in terms of big O. So let's talk a little bit about an AVL tree's performance and just one application. So AVL tree performance. So to summarize, all our main dictionary operations can be implemented in big O of log n time in the worst case. In the worst case, using an AVL tree. Now, I should stress that there's other kinds of self-balancing trees out there. I already mentioned one. Another self-balancing tree that exists is the red-black tree. So red-black tree. Others also exist. I should mention something about the performance. So when it comes to these two different kinds of self-balancing trees, the AVL trees versus the red-black trees. Now, an AVL tree is it's pretty darn balanced. I should stress that the analysis we did before is actually not quite tight. You can make it tighter. But at the same time, when you talk about an AVL tree, because it's more balanced, our get operations, any operations we do in terms of trying to go and find things in the tree is quite good in comparison to a red-black tree. However, a red-black tree is better for insertions than deletions. So if you're doing a lot of inserting and deleting, a red-black tree is a little bit better in practice than an AVL tree. However, if you're doing a lot of queries on the tree, an AVL tree is great in comparison. But their asymptotics are like these operations are the same, generally. That's why I'm showing you only one of the two. So, and I'll say we will see more tree structures later. We'll come back to trees, in particular these types of search trees later. We'll see some more generalizations. One of them is actually quite closely related to the red-black tree. Now, let's talk about an application. So here's an application. Now, I mentioned that you can quite easily augment binary search trees to include duplicates. So one natural thing you could think of is back to when we were talking about heaps. Now, you remember I told you that there is a way you can actually implement a heap using a linked structure, which you can do, and it doesn't have any of these issues involving amortization, meaning that the worst case time complexities are in fact the true ones. However, it almost kind of defeats the point of having to go through that complicated implementation when you can actually come up with a dynamically resizable version of something like that. So one last thing we're going to discuss is an application of an AVL tree. There's many things you can do with an AVL tree. One that you have is sorting. So, for example, if I So we can just use big O of n space as follows. You're just going to perform n insertions. So you build the tree, you create an empty tree, then you perform n insertions. And then you're just going to apply an in-order traversal. So notice that all I have to do is just perform the insertion, then because of the binary search tree property of this AVL tree, I can perform an in-order traversal. How long does the in-order traversal take? Well, that takes linear time, right? The n insertions, that takes n log n, big O of n log n. So you could do the sorting in big O of n log n, and you get something kind of comparable to some of the earlier things I was showing you with heaps. Remember, the heap you can get away with sorting with less extra space. However, the big perk with this is I don't have to use a big complicated linked-based implementation of a heap. Instead, what I can do is I can dynamically resize my structure. So this is a dynamic data structure. So if ever I want to just get a sorted list of all of these, I can just dynamically insert or remove elements from my tree. So the big perk is that this is dynamically resizable, and it's not coaxed into being an array or being that it has a very specialized structure that requires maintenance beyond just this binary search tree property and the height balance property, okay? It's really not, this is actually quite ideal. So you can do the sorting operation trivially with an AVL tree because of the binary search tree property. Does everybody see that? So you just do an in-order traversal on the tree, but you can add and remove things quite naturally from this tree. Okay? So that's all I have to say about AVL trees. Let's move on to a new topic, and this one I've been looking forward to talking to you about for quite a while, actually. Be prepared, I'm going to draw a lot of pictures. So we're going to talk about our next topic, which is the following. It is graphs. So what is a graph? Now, before I actually get to that, I should explain that a graph is a fundamental combinatorial object. I've studied and throughout many aspects of the mathematical sciences. So computer science, graphs pop up all over the place. Mathematics, naturally, graph theory, stats, a whole lot of places graphs are quite prominent these days. So you should not undermine the importance of this combinatorial object. They're quite a great study, and they still quite often are. Many of the problems you will encounter in a computer science program are graph theoretic problems, which it comes out quite naturally. So I want to give you some examples of how these types of problems could possibly pop up. So the first thing you might imagine is you could have a computer network. Imagine I have a bunch of computers. So I have a bunch of computers here. Naturally, these computers are connected to some network. And these networks are indeed connected together. Can you give me a big example of one such type of network? Can you think of something that naturally kind of fits the structure? You can think of the internet. The internet is quite naturally a big network of machines with a backbone that transmits information over servers to clients in all sorts of many other ways. So this is a computer network right here. So these are, you can think of these as servers. These are your clients or just machines that are connected to the servers, okay? So this naturally is one way a graph might manifest itself. So for example, this actually has a much simpler structure to it. Instead, you could just, instead of looking at these as servers and clients and stuff, you can imagine the connectivity of the servers and the computers in a very simple representation. Where I can label each one of the computers or servers or these guys here all as these circles. These circles are what are called vertices or nodes. So these are, so actually I should be very careful here. A single one of these is called a vertex. So this is a vertex or node. They oftentimes, depending on the context, one tends to be more prominent than the other. It's worth noting that plural of vertex is vertices. So don't, if I catch you one day and you're writing vertex is, I will have nightmares, okay? So don't write vertex is, it's vertices. And these connections between the machines and these different machines, these are called, depending on the context, these are edges. This is an edge, a link, or an arc. And the plural is obviously edges, links, or arcs, okay? So you can see that I can represent a fairly complicated structure with actually something very simple. And you would naturally have labels on each one of these. So I maybe call that one B1, this is B2, this is B3. Let's call this one B4. Which one should I call B5? I think it's fun to put that one as B5. This is B6. Let's make that one B7. And then we have V8 and V9. So this is an example of a graph. I'll define what a graph is actually in a little bit. I want to motivate this more with more types of things that you can model with a graph. So let me get some more space. Let's draw some more pictures. So computer network is quite natural to model as a graph. What other things? Now imagine you're doing some traveling between different Canadian airports. And I've just kind of cherry-picked some. I don't claim this to be geometrically correct in terms of what I'm going to write down. It's worth noting that the structure of the graph typically is what matters most, unless they have some special meaning. So it's really the structure of the graph that really matters in many applications. So how they're connected. But that isn't necessarily true all the time. So what I'm going to do is I'm going to label each one of these as a different airport. I'll let you guess which ones are which. You know the names of some of these airports and their abbreviations. I'll give you a hint. The further west we go, the more west it is. The more east we go, the more east it is. So what I'm going to do is I'm going to connect all these airports if there exists a flight between them. So say you want to take a trip from Vancouver to Halifax, there has to be some way for me to do that. And I can do it through various airports. So, for example, I can go from Vancouver to Winnipeg. That's Winnipeg. that's Calgary, by the way, Winnipeg to Toronto to Halifax. I could potentially go through Calgary to Montreal to Halifax. And you might naturally want to represent these edges with distances, the distances to travel between them. And by the way, I did actually calculate these roughly out. So these are rough estimates. That's what I do. 1, 3, 6, 8, 3, 5, 0. Like I said, it's not going to be geometrically correct. So you don't want to necessarily look at a graph and say, hey, look, you didn't draw them close enough to each other. The point is that these edges will have distances that are counted as so-called weights. I'll talk more about weights when we talk about a given problem, a so-called shortest path problem. So if I wanted to figure out what was the shortest route from, say, Vancouver to Halifax, what I could do is I would try to determine the shortest path by looking at the weights on each one of the edges and try to determine the shortest route by summing those weights so that I find the shortest route, okay? Now, obviously I don't claim this to take you the shortest amount of time because naturally at airports, you might have to sit there for a number of hours, okay? So, you can naturally look at this as flight routes with distances. That's quite natural, right? You can represent the connections between the flights as literal connections in a graph, where each one of the edges has a weight, meaning that that is the distance that I'm modeling with the graph. And if I want to compute the shortest path by metric distance, I can always do that. So here's the definition. Big bang, here's the definition of a graph. So, is a pair VE, capital V, capital E, where V is a set of vertices where singular, that's vertex, or you can also call them or nodes. I'll typically use the phrase vertices. And E is a collection of pairs of vertices. Which I'll write with rounded parentheses U comma V. And in certain contexts, this U comma V will change, so just be aware of that. What are these called? These are called edges. Edges, links, or arcs. So, edges, links, or arcs. So, I should note a couple of things. So, usually I use N to denote the number of vertices. So, this is the number of vertices. If you're not familiar with this notation, it's the cardinality sign. This is meaning that, so this notation tells me how many elements are in this set. So, this is the number of vertices. So, N is going to be the number of vertices. And M is going to be the number of edges. So if ever I use N or M in this next while, it's going to be referring to the number of vertices and the number of edges. Because the size of the graph is dependent on N and M. The number of vertices and the number of edges. So just to give you an idea of the flavor of this, I'm going to start talking about different properties of graphs. And let's start with talking about edge types. Because as you see in my examples, I have drawn different types of edges. Here I have arrows. And the other ones, I just kind of just drew a line, right? So let me talk about edge types. So let me first, you're going to find I'm going to be kind of laying some jargon on you as we're going along. So there's very often a way graph theorists talk about different types of things involving graphs. I just want you to be aware of the phrasing here. Because when you just talk about graphs, you have to talk about it in terms of this type of phrasing. Not every graph textbook, for example, uses the exact same definitions, but they're pretty similar. However, some of this verbiage is quite common. So I just want you to be aware of it. So given an edge, E is equal to U comma V. U and V are the endpoints or end vertices of E. So why do we call it endpoints? Well, imagine you have an edge, looks like this. So this is an edge. What are these? These are the endpoints of the edge. Do you get it? So this would be U, that's V. So those would be known as the endpoints of an edge. So there are different kinds of edges. So there are different kinds of edges. And I'm going to give you some examples of different kinds of edges. So there's a couple edge types. So the first one is an undirected edge. This is the most common one you're going to probably run into, an undirected edge. So an undirected edge. So this is an unordered pair of vertices, U and V, often denoted, when I say denoted, I mean often written as, U comma V with the curly braces. These curly braces are notation from set theory. So this is just saying that U and V, if I switch these two around, it doesn't make any significance towards what the edge is. So if I wrote down V comma U with the curly braces, it means the exact same thing as U comma V with the curly braces, okay? Or it uses this rounded parenthesis kind of convention that I use for more general edges. Remember, they're just pairs of vertices. Now, you can use this one or this one. I prefer using this one whenever I can, just to be clear, it's unordered. But if you use this notation, you must indicate that it's an undirected edge, okay? If you don't, then it can be somewhat misleading because somebody might think you're talking about a directed edge, which we're going to talk about next. So just the key thing you need to know is that the endpoints do not matter in which the order you give them, okay? So a directed edge is the other kind of edge I'm going to talk about. A directed edge, you might naturally think, okay, well, what does that mean? It's an ordered pair of vertices U comma V, where the first endpoint, the first vertex, I'll just say first vertex, U, is the origin which is typically referred to in terms as the tail. So that is the origin, and the second vertex is the destination. Otherwise known as the head. I should mention that oftentimes when they're directed edges, they're sometimes called arcs, so just be aware of that. and sometimes called arcs. So I should mention just a little bit of notation for you. If E equals U comma V, then edge E is directed from U to V. So that's a very important phrase. It's directed from U to V. This is abbreviated very often. It's abbreviated as U with an arrow with V. So U, then there's a right arrow, V. So you read that as view is, it's directed from U to V, meaning that there's a directed edge from U to V. Get it? So just one or two more things. So I just want to draw these two types of edges for you. So an undirected edge typically looks like this. So here's U, there's V. There's no arrow or anything. So remember, this is U comma V. So this is U, V with the curly braces. So just remember, the curly braces help tell you really quickly that it's unordered. However, you can use this notation as well. But you just need to make sure you're clear that you're talking about an undirected edge, or what we're going to talk about in a little bit. However, in a directed edge, it can be one of two possible ways. So I can have U, and V, V and U, and I can have a directed edge like this. So if I go from U to V, that means the edge is U comma V. If it's from V to U, the edge is V comma U. So anybody who's familiar with a little bit about set theory would recognize why I prefer using the round parentheses for the directed edges, because the order matters. It helps remind you that the edge's order matters. Like I said, you can use either of these, just make sure you're clear. That's really all I'm saying. So if you get really confused by this, don't worry. You just write U comma V with the rounded parentheses, and that's cool. Just make sure you're clear, okay? Oh, I forgot to close parentheses there. Now, naturally, I need to draw you a picture just to remind you of what all these definitions mean. So I'm going to draw what is called an undirected graph. Okay, so here's a graph. What kind of edges does it have? It has undirected edges, right? So I would just say that this is what is called an undirected graph. Because it consists entirely of edges that are just undirected. So it's G is equal to V comma E. What is V here? Now remember, the vertices are these circles. Or they can be dots as well. Somebody might not necessarily label them for you. They don't necessarily have to be labeled. However, very often in our settings, they will be. So V would be this set, A, B, C, D, E, because those are, oh, I'm missing one. I need F. I need F. So those are all the vertices. How about all the edges? Let's write down all the edges quickly. So these are undirected edges. How many edges do I have? 1, 2, 3, 4, 5, 6, 7. I have 7 edges. Let's write them all down. 1, 2, 3, 4, 5, 6, 7. My curly braces are kind of melting. Just saving myself a little bit of time by writing it out like this. I would recommend writing them from left to right, but I'm just kind of saving some space over there. So let's write down some edges. So we know A comma B is an edge. There's an edge that connects A to B. Okay, how about from A to C, right? A to C. How about A to F? There's an edge from A to F. How about A to E? Look, there's an edge here. How about B and D? There's an edge from B to D. Okay, how about C to D? There's an edge here. How about one last one, D, F. So note that the order, which, remember, the order does not matter here. It's just that they are paired together because they're connected right here. So this is an undirected graph. So let me just write down one last definition, and we're going to wrap things up here for today. So an undirected graph, So I'm going to give you three definitions very quickly. So an undirected graph is a graph where all the edges are undirected. A directed graph, which is often known as a digraph, is a digraph. You can naturally say, okay, well, it's a graph where all the edges are what? Directed. They're all directed. One last one is called a mixed graph. So a mixed graph, as you might naturally think, a mixed graph is simply just a graph where edges are directed and undirected. So the edges are directed and undirected. So that means that the graph might consist of some directed edges. It also might consist of some edges that are undirected, and they may have a special meaning. So we're going to stop here, and when we come back, we'll talk more about graphs. So I'll say thank you very much, and have a beautiful day.